This is part one of 2 lessons on empirical and molecular formulas. In this lesson, we'll be focusing on how we can determine empirical formulas from various types of data. So before we do that, we'll just look at what the difference is between molecular and empirical formulas. So a molecular formula tells you the exact number of atoms in one molecule or formula unit of a compound, whereas an empirical formula gives you the lowest whole number ratio of atoms in a compound. So if we look at an example, the molecular formula for the benzene molecule is C6H6. So in each molecule of benzene, there are 6 carbons and 6 hydrogens. The empirical formula for benzene is just CH. So this tells you that the C and the H are in a 1-to-1 ratio within the molecule, but it doesn't tell you exactly how many of each there are. So how can we determine the empirical formula of a compound when we're given some information, other information about it? So the first one is if we have the percentage composition. So our first sample problem, an unknown compound is found to consist of 40.1% sulfur and 59.9% oxygen by mass. Determine the empirical formula of the unknown compound. So we have the percentage composition, and percent is so much out of 100, right? So if we assume that we have 100 grams of this compound, then we know that we have 40.1 grams of sulfur and 59.9 grams of oxygen. When you're doing these problems, it actually doesn't matter how much of the compound you're looking at because you're going to be going for ratios. So this is just a way to make the math really easy, is just to assume 100 grams of the compound. So now that we have masses, we're going to convert those to moles using the molar mass of the element. So we've got 40.1 grams of sulfur. The molar mass of sulfur is 32.07 grams per mole. So we get that we have 1.25039 moles of sulfur. And at this point, it's important that you don't round that number too much. Maybe keeping 5 decimal places is a little excessive, but it's better to be excessive than to round. You certainly do not want to round this to 1.3. And then we do the same thing for oxygen, 59.9 grams of oxygen. The molar mass of oxygen is 16 grams per mole. So we get 3.74375 moles of oxygen. And again, you don't want to round this too much because we're not done the question yet. So those are the 2 numbers that we got for moles. And so the next step we're going to do is we're going to find the whole number mole ratio by dividing all the mole amounts, in this case there's only 2, by the smallest mole amount. So the smallest mole amount is the 1.25039. So for sulfur, 1.25039 moles divided by 1.25039 moles is going to give us 1. And then for oxygen, we again divide by the smallest number, and we get 2.994. So what this tells us is that for every 1 sulfur, there are 2.994 oxygens. And at this point, you can round, and you want to round to a whole number, but only if it's really close to that whole number. If you get something like 2.8, that's not close enough. It's got to be close, and 2.994 is close. So we round that up to 3. So that says that for every 1 sulfur, there are 3 oxygens. So we can now write the empirical formula as SO3. Next sample problem. An unknown compound is found to consist of 50.81% zinc, 16.04% phosphorus, and 33.15% oxygen by mass. Determine the empirical formula of the unknown compound. So we're going to follow those same steps. We're going to assume we've got 100 grams. So we use the percent composition to determine a mass for 100 grams. So we just take those percents and change them into masses. And then we're going to take the masses and convert to moles. So for zinc, we've got 50.81 grams. The molar mass is 65.38 grams per mole. So we're going to divide, and we get 0.77715 moles of zinc. Same thing for phosphorus, 16.04 grams of phosphorus. Molar mass of 30.97. We're going to divide 0.51792 moles of phosphorus. Same thing for oxygen, 33.15 grams of oxygen times the molar mass of oxygen, or times 1 over the molar mass of oxygen. So we're dividing by 16. We get 2.07188 moles of oxygen. Okay, so this tells us that for every 0.77715 moles of zinc, there are 0.51792 moles of phosphorus and 2.07188 moles of oxygen. But we're not going to write that in a formula, right? We want nice whole number ratios. So that's why we do this next step of dividing by the smallest, which in this case is the moles of phosphorus, 0.51792. So we divide the moles of zinc by that number, and we get 1.5. And so here that's not close enough to 2, so we're going to leave it at 1.5. For phosphorus, we get 1, and for oxygen, when we divide, we get 4. So now we know there's 1.5 zincs for every 1 phosphorus and for every 4 oxygen. But again, we need whole numbers. So if at this point you don't get a number that's really close to a whole number, say it's close to 0.5, then what you need to do is multiply all the numbers by a least common multiple that will make the decimal into a whole number. So in this case, if you multiply everything by 2, everything becomes a whole number. So the zinc goes to 3, the phosphorus to 2, and the oxygen to 8. So we get, now we can write the empirical formula of Zn3P2O8. So at the point of the dividing by the smallest, you want to be careful about your rounding and make sure that you're close enough to a whole number. If you're not, you look, okay, am I close to 0.5? So then you would leave it at the 0.5 and multiply by 2. Or maybe you're close to 0.33, and then you could multiply by 3 to get whole numbers. Or in very rare occasions, you might be close to a quarter, right? So like 1.25, and then you'd have to multiply everything by 4 to get to whole numbers. Okay, so you have to look at the numbers you have, and if you get something completely off from that, chances are you made a mistake. So since an empirical formula involves relative amounts of the elements, any mass of the compound can be used. Thus, rather than being given percentage composition data, you may just be given experimental mass data. And in this case, you can just skip step 1, which was really just changing a percent to grams, and you just use the masses directly in step 2. So our last sample problem determined the empirical formula of a compound that is experimentally determined to contain 17.47 grams of iron and 7.53 grams of oxygen. So you're going to take those masses, and the first step is convert to moles. So we use the molar mass of iron to get 0.3128 moles of iron, and the molar mass of oxygen gets us 0.4706 moles of oxygen. Next step is to divide by the smallest number of moles, which is the 0.3128. So we divide both of those by 0.3128. So for iron, we get 1, and for oxygen, we get 1.5. Remember, we want whole numbers, so we're going to multiply both by 2 to get us whole numbers of 2 and 3. So therefore, the empirical formula is Fe2O3. So that's the method you can use to figure out the empirical formula for a compound when you have percentage composition data or mass data. In part 2 of empirical and molecular formulas, we'll look at how you can then go to the next step and actually figure out what the molecular formula for a compound is.